It's about 40 minutes away. And our site is part of the Global Innovation Campus, where we have our synchrotron, the Institute Lab, which produces neutron beams. But we have about 30,000 people on this site here, working between 8 different institutes doing different types of science. We're on the international site down here, and then there's the French part of the site down here with the CEA, the CNRS, and other institutes and facilities. Like Sesame, which I'll tell you about in a second, the ESREP is international. We're pleased to have 22 countries now on board. India joined a couple of weeks ago. Down here at a low percentage, but nonetheless they are an associate partner now in the ESREP. We've got 13 members up here, the big ones being the usual countries, France, Germany, Italy, United Kingdom. We're very pleased as well that I said these places are intercultural hubs. We have 40 different nationalities in our staff contingent at the ESREP, which is not bad. We have 6,500 users coming to use the ESREP every year. Out of those 30,000 strong European community using light sources. We're a private civil company. Anybody can apply for beam time. Once you apply for beam time, like many of the other facilities across Europe, the access is then free. You apply, you get access based on scientific excellence. You go through, you publish the work, but everything is free. If you want to keep the results confidential, you give me a ring, you get your checkbook out, and then you pay for access, and then we work with industry. We generate about 2 million euros a year working with industry. We're going through an upgrade now at the ESREP. I was responsible for setting this up. It's worth about 300 million euros. We've made extensions to the buildings, and 2nd of December next year, 2018, we will close down for 18 months. We'll chuck away the old accelerator, the old storage ring, and we'll install a new one. We come back to operation in about August 2020, with about 2 orders of magnitude increase in work that we can do. So even more X-rays, even more coherence, even better spatial resolution. These are most of the European light sources, the big ones. There's actually more than that. There's some that fit in this room here. But these are the principal ones, the ESREP, DESI in Hamburg, this is Alba in Barcelona, I think I'm getting it right. I think this is Swiss Light Source. But there's 9 covering different countries. And we're now pleased to welcome Sesame over in Jordan as one of these facilities. So Sesame is a synchrotron. It's a little baby one, and it's just starting operation. It's an intergovernmental cooperation again with, as I said, a group of countries, including Cyprus, many of which wouldn't normally collaborate or work together. So it's supported by UNESCO, and it's been developed under the umbrella of UNESCO, with funding coming from a variety of places, including the European community. It's based in Jordan, just here, not far from Israel, not far from a number of countries where there's interesting things happening at the moment. Open Sesame is a grant that's being given by the European Union worth 2 million euros. The aim of this is to transfer knowledge from the European facilities to help Sesame unlock its potential for the Middle East countries. So it takes time to build up communities that can use these synchrotron sources. But what we want to do is try and accelerate that for Open Sesame so that the facility can serve scientists in the Middle East. And when I was at the user meeting in December last year, the enthusiasm from the people that were present at that meeting, there was about 200 people there, was just amazing. And it was great to see staff, scientists from different countries sitting together, talking together, each other, again, sitting around tables where they wouldn't necessarily otherwise be able to meet. Our concrete objectives are, in the Middle East, there's not necessarily all the staff skills available to run a synchrotron, so we want to be able to try and enhance those by exchanging how we're working in the European facilities. Build up the capacity in Middle Eastern researchers to be able to optimally use this synchrotron that's coming into operation now. And to support Sesame as a research infrastructure in building its visibility and how funding agencies perceive the facility within the Middle East. I said we got 2 million euros. The project started in January this year. It's lasting to the end of 2019. This is the website, which will be active in about a week or so. These are the partners. They're widely spread across Europe. So I think there's 11 of us. Many of them are the national or international synchrotron facilities, but we've also got Instruct, which is a network across Europe for structural biology. We have the Cyprus Institute down here, which we're very pleased to have on board. Of course, Sesame itself, and CERN. CERN has been helped supporting Sesame a huge amount with provision of magnets, which are a critical part of the accelerator assembly, and other technologies. Although the ISREP is the coordinator of the project, the actual needs and the interest of the project are driven very much by Sesame. They're telling us what they want, and we build the project around their needs and expectations. So as part of this, we've got Wolfgang, who's part of the Training Advisory Committee of Sesame involved. The deputy coordinator is based at Sesame, and we have Georgios and Yasser, two of the directors of Sesame, who are part of the project executive board and coordination. But because it's so linked to Sesame, Sesame's only just starting now. So they've only just successfully circulated electrons, putting energy in through RF into the electrons and keeping them circulating. The inauguration is on the 16th of May, when I think they're hoping to have had their first flight. So the machine commissioning is ongoing at the moment. This is January this year. The machine is gradually being commissioned. These represent, you can't see this, but these are different beam lines coming into operation. So they're firstly having an infrared beam line, then X-ray fluorescence, and then there's some other beam lines that will come up as funding becomes available. They've already issued their first call for proposals, where they are asking for proposals for beam type in autumn this year. So what I'll do is just quickly go through some of the key objectives and a little bit more details about what we're trying to do. So one of the key things I mentioned was training Sesame staff. Again, staff in the Middle East for running a complex accelerator complex together with the beam lines, the computing and the instrumentation. It is not necessarily fully existing today. So here this is really to try and get the optimal use out of the facility. And there is funding for 65 staff exchanges between Sesame and going out to the European facilities. That's starting already. So there's 39 staff going from Sesame to Europe and 26 from Europe to Sesame. And actually, the number of Sesame staff is quite low at the moment. I think there's only about 60. So the actual percentage of Sesame staff that benefit from coming out to Europe is very significant. And this is going to be focused in areas things like safety, beamline instrumentation, cryogenics, sample environments, user administration, how to actually run a facility with users. As I said, at the ISREP we have 6,500 coming through per year. So the administration and the travel and the work behind that is not insignificant. A key goal as well is to actually tell and teach researchers within the Middle East, members of Sesame and beyond, how they can actually use the X-ray beams, the infrared beams that are going to be generated at Sesame. So for this, we're arranging a number of thematic schools, which will hopefully touch about over 100 researchers from the Sesame region, where we'll be focusing on different topics that are relevant, especially to the Middle East. A key part, this is sort of a little bit different. The key part of these research infrastructures is actually being visible, showing off what they can do as intercultural hubs of the training, because there's a lot of money going into these places, and the impact that they have is very, very important. And especially in the case of Sesame, given its specific role, specific set of members, the visibility of what it is doing and what it is achieving in terms of the science and bringing countries together is very important. And we'll also be hopefully having an impact in the communications and media training for the Sesame staff and their users. At the inauguration, there's the BBC is expected, there's French broadcasters, German broadcasters, so it's important that Sesame can actually enable the best use of this kind of work. These are some of the people actually running this, because it actually does very much work, which is good. Nazari's got an extremely challenging task with the exchanges and how we organize it. These are focused, as I said, on a number of different areas, exchanging going from beamline techniques through to the commissioning, general skills in technicians, in how to run a cryogenic plant, how to run and install X-ray optics, safety as well. These things are not necessarily trivial to run from a safety perspective. There's an accelerator, there's vacuum, removing windows, there's all sorts of risks involved, and this also is a key topic for working with. As well as I mentioned, the user office and user administration. The schools are being run by Miguel, who's the scientific director of Alba in Spain, with Giorgio, who's the Italian director at Sesame. There's 4 thematic schools. One of the first one coming up, and it's being developed at the moment. We're very pleased it's going to be hosted in we hope, we're 95% certain, depending on what happens, that it will be hosted within the CaSToRC library in Alexandria. And this will be focused on cultural heritage and ancient artifacts, which is a huge topic in the Middle East, as well as in Cyprus, I think, where synchrotron sources have an important impact in this area. This area did not exist as synchrotron sources 10 years ago. And it's jumped like this as scientists working in this area realize the power of what the synchrotrons can do to look inside materials, to look at the chemistry. And that's important because some of the first beam lines coming up at Sesame are infrared, X-ray powder diffraction, and X-ray fluorescence. And these are key techniques for looking inside and around ancient artifacts. Everyone on biological and biomedical applications, especially IR infrared microspectroscopy, which allows you to look at tissues and individual cells and see what goes on. Diamond's been doing some beautiful work on individual cells, looking for cancer signatures using infrared spectroscopy, trying to identify cells that are cancerous. Structural biology is a huge area of synchrotrons. A large chunk of the case for Diamond in the United Kingdom was based on structural biology alone. We sell €500,000 worth of services for drug discovery every year at the ISRAF. Another important one is environmental sciences, where again the topics of the first beam lines coming up at Sesame have a direct impact in this area, where you can look at things like recycling, better use of raw materials and pollution, and doing speciation of elements. So things like cultural heritage and for ancient materials, the key things about synchrotron light is non-invasive. If you go to the hospital and have your X-rays on your hand, they have to chop your hand apart to look inside. The X-rays can look through and they're non-destructive. So you can put a whole object onto the beam line and look through it. We have a very high chemical sensitivity because we've got a lot of photons measuring what's going on. We can focus the beam down for a high, that's 100 meter shot. I passed my time. Maybe there was a time. We can focus the X-ray beam, so there's very high spatial resolution. We can get down to 20 nanometers or so using X-ray beams at the ISRAF. So you can map them. You can do elementary mapping on a very fine spatial resolution. And you can also probe with a huge range of techniques. So you can do X-ray powder diffraction, but then go to another beam line and add infrared spectroscopy to it as well. Now, just a few examples. This is work that's been done by Marine over at the ISRAF. This is Chinese porcelain. But one of the questions was, how did they actually produce the blue color? What's the exact chemistry behind it? And you don't want to be chopping these things up to look inside. When using 3D element mapping, you can look through the glaze and understand the chemistry of what's going on with the cobalt blue coloring. So you can look at speciation of the cobalt, but you can do that in 3 dimensions at a very high spatial resolution. This is the Van Gogh's sunflowers. It's very yellow. The yellow paint is based on lead chromates. And according to the different mixes of lead chromate, you can get different types of yellow color. This has also been known for centuries. But the lead coloring degrades with time. So what we now see in Van Gogh's picture is not how he painted it in, I don't know when it was, 1800 and something years. And part of the problem, as I mentioned, is that with light, the colors change. Only subtly, but it can dramatically change the look of the painting. So this means that if we could detect what the chromate, how it's aged, you could artificially color the painting and understand what it would have liked when you did it. But also importantly, you can look at conservation and try and optimize the color of the lights that are illuminating the painting so they have less damage in time for the pigments. And that's an important piece of work in terms of conservation within art galleries, where you want to ensure these paintings have longevity and you keep the coloring as accurately as you can, as it was when it was first made. This is similar work, not from something that's hundreds of years old, but something that's only now half a century old, where the polymers used in objects from the 1950s are very fragile. And they also age poorly, and there's understanding there of what's happening with the chemistry using X-ray beams. An older example, this is a papyrus that was burnt a long time ago in one of the, I think one of the volcanic eruptions. And you can't touch this, right? This is burnt paper. You touch it, it crumbles, you lose the information. Using X-ray technology, they looked at the ink to understand what the chemistry of it is, what the structure of it is, They've also done 3D tomography. You may have seen this, where they've done 3D, like going to hospitals, you do a CT, right? You get a 3D picture of your hand or whatever it might be. We've done that at very high resolution, but because of the structure of the ink, you can actually reconstruct that and start reading that papyrus from the inside out without having to destroy it. There's no other way to read that. That's an immense computing job, actually, because actually harvesting the data there doesn't take very long. But then organizing that so you can actually read on the rolled up papyrus and try and reconstruct the writing is computationally not trivial. There'll be young researcher training. Hercules is a well-known name within the research infrastructure world, and there'll be a specific 2-week course at Sesame later in the project. And we're also just launching now opportunities for researchers, young researchers from the Middle East, members of Sesame, to come and visit for between 4 and 12 weeks in European facilities. And that's now actually open. Miguel's just opened the call. We open from, I think, the 1st of May. Where there's up to just under 10K available for people to come over and visit our facilities. It's kind of all my domain. So again, when you think of any type of material, even if it's like sort of trivial, like ice cream or margarine, the work we do in the facilities can help industrial innovation. So at the ISRF, we've got about 150 clients, some of whom don't allow us to say who they are. These are some of the names that allow us to say who they are. You might recognize some of the names there. But industrial innovation in these facilities is growing enormously, and the pressure from our funding agencies to work more, I don't know what it's like within the computational world, but certainly in our world, there's pressure from our funding agencies to work more with industry and show more economic impact and show more relevance to applied research. So at the ISRF, we do €2 million a year, and we estimate about 30% of the peer-reviewed research has some link to industry. A few weeks ago, last week, in fact, I think it was, 21st of April, we had Johnson Matty, who's just here, who will be using the ISRF on 3 beamlines on the same day, which has never happened before. We were really pleased about that. They had a proprietary paid-for access, and they also had some academic access in their case, looking at different types of catalysts. So one of the important aspects of Sesame will be international industrial exploitation. So we will be working with them to build a contact list, and then work out to relevant industries in the Middle East. An obvious one will be petrochemicals because of the, obviously some of the work is being done in the Middle East, but there'll be others as well. There'll be a workshop in winter 2019. An important part of what will happen in Open Sesame is directly linked to the Cyprus Institute, where a lot of the work I just showed you there is going to produce an enormous amount of training materials. The outreach to the students, the outreach to the researchers, the outreach to media and what have you. And Cyprus Institute has promised with a deliverable soon. Harry, I've lost him. There. We have a deliverable milestone, please, in April, where the warehouse should be at least functional in some way, which is now right. So Cyprus Institute is building a warehouse to deliver this technology across the Sesame members and beyond, so that this will be available during our project, but also has existence after the project is finished. So all that training material can be distributed through an online warehouse. And realistically, amongst the Sesame members, I think Cyprus is the only realistic host for this, given the internet bandwidth and the technology here. And some of the files will be quite large, there'll be some videos, there'll be PowerPoint and other things, but small scale compared to big data. The last thing is communication strategy. CERN has already been working on this with Sesame for a number of years. James, who you saw just flash up there, 50% of his time is dedicated to supporting Sesame's outreach activities. And so this is actually quite important because Sesame has a huge visibility in terms of the world media. And part of the work that we're doing is trying to build a pilot film by this UK production company, which will hopefully lead into a full-scale documentary on Sesame with a major broadcaster somewhere in the world. Cyprus is also doing the roadshows. So part of the important aspect of getting the message out about Sesame is to go to the universities within the members of Sesame and tell them about the opportunities of what's going on. This is much more in a general way. It's not the targeted training that we've talked about, but here this is one roadshow event of each Sesame member, although Bahrain is now not part of the roadshow list at the moment. Bahrain, I think, has stepped back from involvement in Sesame, so we have an opportunity to go somewhere else as well then. So I think Sesame will advise us perhaps where we might go, but they're also targeting other countries in the Middle East that could become involved. I think well, there's a number of possibilities there. So here there's a presentation of Sesame and what's going on with Sesame, and importantly, how to access, how does it work for the students and the researchers that might want to have an access. I think you've had one in Egypt so far, and there'll be other ones coming up. A key part of these research infrastructures is how to run them. It sounds a bit trivial and naive, but the administration of running these things on an international basis is not easy. Having young, trained people moving up into these positions is an important aspect of the value, actually, of these research infrastructures. So part of the work that's being done here by DESI is the German synchrotron based in Hamburg. We're looking at training the next generation of administrators, because they're the people that in 10 to 20 years' time will hold the funding strings to continue supporting Sesame and perhaps doing other research infrastructures within the members of Sesame. So there'll be 2 training modules for this kind of work based on RAMIRI, which is an old funding program supported by Europe for realizing and managing international research infrastructures. So this is just to recap, this is the main gang involved in running the project. These are our emails. If you want to get in touch with us, don't hesitate to harass us. We'll be pleased to hear from you. And thanks for your attention. Questions? Any questions from computing people? Is that computing people?
There are some physicists here.
Well, there's some physicists. The physicists didn't get to be physicists earlier.
So there are no questions. Let's bring our speaker again. Questions with there's now questions also.
Okay.
So now we're gonna listen to HPC and Big Data and use cases from the VSIM project. The first speaker is Marie, who's gonna talk about life sciences.
So I'm a member of VSIM. I am the head of the life sciences scientific community, and I'm going to talk today about how life sciences can benefit from e-infrastructure such as VSIM. So yesterday I already told you about the era of personalized medicine, and I'm going to say what challenges do we have in life sciences concerning big data. And then I'm going to talk about some community objectives that we have in VSIM and how we address them with our offered services that have to do with codes, workflows, pipelines, tools. We have regional community data sets and application level services as well as training. And I will end with some examples. So yesterday I gave an example about personalized medicine and how we turn medicine to provide the right patient with the right drug at the right time. So we don't apply generic drugs anymore, but we consider specific patient groups, what kind of disease they have, and we manage a lot by also using Sesame and synchrotron resources to provide personalized medicine for diagnosis, treatment, dosage, and accurate prevention of disease. So one of the goals of the VSIM infrastructure is to provide long-term, of course, targeted therapies for Southeastern and Eastern Mediterranean populations, Southeastern Europe and Eastern Mediterranean. And this is an example that I brought up yesterday. It's this, these patients with lung cancer that are only 4%, but still they have something very common. They have a mutation in a specific protein. These patients are below 45 years old normally, and they are not smokers, but still they get lung cancer. So we could identify which protein is the cause of this disease, and using synchrotron resources, the researchers crystallized and visualized the protein, and they could apply drug discovery principles in order to make a specific drug for this specific target, of population. So here are the green people that you see here for whom the medicine is safe and effective. So the challenges basically that we have is that we have such exponential growth and availability of such kind of data, like the data I showed you before. Because this kind of data is coming from genotyping of people, for example, from next generation sequencing. We have such enormous data from patients that we have to use somehow. So these patient sets are large and they're very complex, and processing them is quite laborious. So we need to find new methods to process and make this data useful. So we have different challenges for data analysis, including all this. I'm not going to go through all this list. I'm sure you've heard of what big data is about. Capture, traces, analysis, search, sharing, storage, transferring. We discussed a little bit about that yesterday. I said that we are producing terabytes of data and we don't know where to store it, how to transfer it. Also, someone asked me yesterday, oh, are you sharing your data with other groups, and can other groups benefit from the terabytes of data that you generated so that you actually don't have this fragmented information, which is one of the challenges that we have. So we need a federated platform to give unified accesses to the users. Okay. Using computers for life sciences is extremely useful. So it has facilitated biological data analysis, and computers in biology have enabled better understanding of biomolecular processes. So now, taking together the challenges and the advances in the computers, the overall goal of the life sciences in this particular region is to integrate and analyze data from patients in order to identify patient groups that will benefit from these targeted therapies. So we want to create and provide the necessary services for understanding disease mechanisms. Okay, so basically, this is a summary of our goals. I already discussed it, but I'm going to give an example so that it's a little clearer here. So for example, one example would be to analyze dominant cancer mutations in populations in Eastern Europe. We have available data sets. For example, the University of Belgrade in Serbia, it has data for 6,000 patients from this region. So we can analyze these data sets by using integration of data within this virtual research infrastructure that could relate to regional characteristics and assist us to get novel therapies. So based on what I just said, we have separated different areas of applications in life sciences in this scene. And this is modeling and molecular dynamic studies of important drug targets. So basically taking the data from synchrotron, from crystal structures of proteins that are implicated in disease in this area, just model it in order to understand better the dynamics of these cancerous or otherwise implicated in disease proteins. Then perform a drug design. Of course, analyze, and this should be actually first, analyze next generation sequencing, which will enable us to identify which of these data comes out of proteins that are implicated in disease. Synchrotron data analysis, okay, we have the information, so of next generation sequencing. Now we need to go to the synchrotron and actually visualize this protein. Which are these proteins that are cancerous? We need to see the picture. And after we have the picture, we can do this analysis. Of course, another very important part is image processing. So if we have MRI images from patients that have cancer or other diseases, we can analyze using computers and image processing and understand better the disease. And also analyzing DNA and RNA from patients. So for this, we have made different codes for these areas that we aim for people in the region to submit their applications to the infrastructure, and the research groups can provide their applications in these type of areas, and they can get access to the services of the infrastructure that I'm going to describe in just 1 minute. So at the moment we have 12 research institutes from different countries of the region, like you can see here. So Greece, Montenegro, Jordan, Serbia, Bulgaria, FR, Macedonia, Jordan, Armenia, and Cyprus. And through these core institutes that we have in countries, we have developed an infrastructure that gives access to codes that I'm going to show you. It gives access to workflows, pipelines, and tools. It gives access to regional community data sets and application level services. So the first thing is the codes. So you see here several programs. Okay, so most probably you cannot recognize them, but if you trust me, I will tell you that these are the most commonly used programs in the life sciences application, computational life sciences. So this is the one offer that we are giving, so that these codes are installed and can be used by anyone who wants to use this infrastructure within. The second that we are offering is these workflows, pipelines, and tools. And I have, you see here these integration phases, so these 12 countries that 10 countries, 12 institutes that I discussed, they are all, each one giving different workflows, pipelines, and tools. Okay, here it's a little, the letters are small, but basically we are giving very structured tutorials or workflows or different tools that can be used to analyze data from the areas that I described before. So molecular dynamic simulations, computer-aided drug design, next generation sequencing, and all the areas that I discussed. So okay, here is a list. I think the slides will be available. So if you are interested in any of these workflows, you can actually go and download them. Everything is online. I think the slides will be provided. The third service that the life sciences scientific community is providing is the regional community datasets. I already said before that there is this database of 6,000 patients from Serbian population that will be shared, and at the moment we have also data. For example, all the data that I shared yesterday in my presentation, they are all available in this link here, so you can download this simulation data. Someone can post-process it. This is a huge amount of data that is available. For example, you can see here this oncogenic protein with 2 mutants as a molecular dynamics trajectory. All the data is available. And we have also other mutant proteins that are available. These are coming from Greek populations. And okay, some more data sets. So everything that is produced in this infrastructure, we ask that users, after the end of their calculations, they submit it to the virtual research infrastructure, and it's available for everyone. The third thing that we are providing is the fourth thing is the application level services. Oh, sorry. Is the application level services. So we have several programs implemented as web servers. So useful tools for analysis and post-processing of data in life sciences, they are becoming now available in this same project. And I'm going to go one by one. First of all, we have this CaSToRC server, which is a web-based pipeline for filtering, clustering, and analyzing compounds for drug discovery. And okay, this is a lot of text, but I'm going to explain it more graphically. Basically, it's I showed this slide yesterday. So we start from synchrotron data, crystal structures, and the visualization of proteins, and we do the drug design process. I'm not going to talk about the drug design because I said it yesterday. But after the drug design process, we end up with thousands of compounds from where we should select just a few compounds to be used for experimental testing. And this is the experimental assays that I was saying yesterday. In this example, we have 2 million compounds, chemical compounds. They go through a filter, okay? But even after going through the filter, we still have 1,000 very promising compounds. And we end up selecting a magic number 30. How do we go from 1,000 to 30? The way it used to happen was that a chemist or a researcher would go in the computer and visualize 1,000 compounds inside the mutated protein, and somehow with chemical insights, I don't know how, choose 30 compounds. But this is very time costing and not very efficient. So how we're going to select these compounds? We created this tool, this post-processing with CaSToRC server, which calculates, first of all, toxicity of the compound. Because one thing that is important when you're selecting compound is the toxicity. The second is this van der Waals constant, basically context, is how promising the structure is of the molecule. And also we want to cluster the compounds based on chemical similarity so that we have a range of different chemotypes. So basically this is the CaSToRC server. It's available on vSim. What you can do, you have here in this menu different things that you could do. For example, you can browse these compounds, so you get it out from the program. Now you need to post-process it. The first thing is you can browse it, and then you have different filtering steps. So here I'm showing this van der Waals filtering. Here you see the compound in green, and then you have the protein in this kind of representation, the serpentine. And you see here that I have circled a region of the molecule that is not correct. Basically, the algorithms can make mistakes. And this platform identifies where the algorithm is actually clashing the molecule with itself. Another important thing is toxicity of the molecules. Some molecules that are coming out of our screening may be toxic for humans. And I'm showing here some toxic fragments. And we actually have libraries of fragments of molecules that have toxic nature for humans. We have encoded this through chemoinformatics inside ChemBioServer. So if you submit your compounds here, ChemBioServer will tell you, oh look, this compound contains this benzoquinone, which is known to be mutagenic. You don't want to have this in a drug, so please don't use it. So ChemBioServer will give you this information in the toxicity filtering section, okay, which is you can see here. And then the last thing that we want to do is, after we have filtered thousands of compounds, we need to cluster them according to chemical similarity, because it is known that similar structures will have similar activity. So you don't want to go and buy 30 compounds that have the same activity. You want to buy different chemotypes. So ChemBioServer is clustering compounds here, and it gives you different groups of compounds. So from these clusters, you will select one compound from this cluster, one compound from this cluster, in order to have as much diversity as possible. So now this is one of the tools that we are providing. I'm sorry, I'm going back to another tool now, which is called AFMM, and this is a parameterization tool for molecular dynamics simulations. So you have basically different drug molecules that you want to simulate. Parameters are not available for every possible drug molecule, so you need to create parameters. So this is one tool. This is a workflow where you are applying quantum chemistry and molecular dynamics for generating parameters. So you can also find this it's a web server. You can find it here. Okay, this is the interface of this AFMM force-field parameterization program, just providing parameters for drugs. Another application that we are giving in, oh, I'm sorry, this is the wrong link. I'll make sure to correct it before I send it to you. It's a web server to create nanoparticles. And you can see here different nanoparticles, okay? So I'm going to go a little fast because I'm being given notice. I only have 2 minutes. This is another web server. So I'm just giving examples of applications that we have, which are very nice tools to use for life scientists. So here we have a tool that measures the volume of the gravity of the binding sites. So easily you can put in your protein, and the algorithm will tell you how big the cavity is, because how big the cavity is will determine whether you can do drug design. And the last thing we offer is training material. Here we have an event in, where was this? Because we had different, okay, this was in Belgrade, and everything has been recorded and it's actually online, and we had another one in Macedonia. Okay, in the last few seconds that I have, I will also say that apart from all the services, we also give access to infrastructure, so actual computing time, where researchers can can perform their projects. So this is a project from Armenia, and it's about protein denaturation using surfactants. So these scientists use VSIM datasets. They use the VSIM scientific application environment and the HPC services, and they perform their studies, which I do not have time to go into, but they studied this protein in presence of surfactants. And okay, due to lack of time, I will just go on, but I will just say that they did publish the results already into good journals, and they are progressing. And this is another example of using the infrastructure for computer-aided drug design. So I'm not going to go through that. So I'm going to finish and say that the life sciences has now an infrastructure in the region that has almost everything, all the codes available that we know for life sciences, several workflows, we have regional community data sets available, and more, we can accommodate more if you have something, application level services and training materials. So thank you for your attention. And yes.
Quick question regarding data.
Yes.
You have some personal medical data. Are they totally anonymized? How do you use that?
Yeah. So yes, there is one service that is called Become. I don't know if the person is here. Yes. So I think he's more suited to answer.
So in our services, we really deal with personal data. And then what we are doing, when we are uploading data to the VCM resources, we anonymize the data. So we remove the personal text actually from the Beacon data. And also when we get the access, we are getting access only without the personal data. But otherwise, we have a portal that have possibility to request access to the personal data. Okay, so it should be approved by a patient, it should be approved by an institution, and also we're working on partial personalized there. So say example, what equipment was used or what diagnostic was done, yeah, but not say the patient name. So we deal with it in this direction.
That was amazing. I had two questions.
Yes.
Your data policy, where the results have to be distributed. Do you have an embargo period if there's a PhD project involved and the results need to be protected for?
Yeah, sure, of course.
Okay.
Of course, we leave this up to the user. I mean, they should give us the data set, but of course, it's a whole mutual agreement, and also the data is distributed with an open license agreement.
Okay, so the second place for industrial companies, they could embargo it for a short period.
Oh yeah, absolutely.
Okay, and second one, I like very much your pipeline going from 2 million compounds to 1,000 to 30. When you mentioned the assays in situ, do your assays on those fragments or compounds include doing the structural biology, or is it more
It depends on the project.
Okay.
And it depends on the complexity of the project, I should say. We always want structural biology. We dream about it, but it's not always possible. So whenever it's possible, we do it. And whenever we have access to such amazing infrastructure like the ones you showed. But it's not always possible.
Okay, maybe there's some links to be made to some other European projects or something like it.
Yeah, absolutely. We have to discuss that. Right, thank you. Yes.
You mentioned about AFFC, quantum chemistry.
Yes.
With conjecturing molecular dynamics.
Yes.
And what is this quantum change model? What it is using for the optimization of the atomic structure, of the calculation of the energetic bands or some chemical
Exactly.
reactions.
You just said everything. It's for that.
And names of this model is AFFC.
FMM. It's all online. I mean, the slides will be available.
The slides will be available, and AFMM next week will be linked on the VIE portal. So once you go to the portal, you will have access to it.
Yes, but the link that I am showing is active, so
It's
you can already use it.
It's already in the service hub.
Yes.
Right.
Yeah.
Okay. There's a link. So yeah, let's thank again. And now, Theodoros Christoudias is going to talk about climate science.
Okay. So good morning, everyone. I'm Christoudias. I'm with the Cyprus Institute. I represent the climate community within the BICIM project. So I'll be giving the same kind of talk that Zoe just gave, but with respect to climate. So this is a brief outline. So I'm just going to go quickly through the goals and objectives of the community because not everyone in this room is a climate scientist, and then some of the research activities that we are pursuing with LINK's team. Since this also relates to HPC and Big Data, I'll just give an introduction to the challenges faced by the Earth system modeling community, the historical evolution, and how we see the future. And then I'll give, since time is short, I'll just give 3 use cases from the BICIM project on using new technologies, so GPUs, to accelerate climate science, opening our data from regional forecasting of the weather, and then some examples of processing big data in situ and with 3D models. So traditionally, the climate community is relying on strong computing, and BICIM tries to integrate HPC resources, grid computing, as well as a distributed data infrastructure. And the idea is to support both the research and also the operational activity in the region. So we try to identify where there are synergies between the BICIM participants, both in geography but also research teams, and we try to integrate the data and computing resources and requirements. So we support a wide range of research activity, and I have here some broad categories. So there's users that deal with regional climate modeling and weather forecasting. We have some applications that are dealing with global climate modeling, and these are needed to then downscale to the regional level. We study air pollution and its influence on human health. And finally, we try to quantify the impacts of climate change on humans, but also the environment and society. And this is done to support decision and policy making. So the research activities are complemented by code development and visualization, which of course is crucial to gain insight from simulation data. So moving to the second part of the talk, the evolution of climate models since the invention of computing or the application of computing for simulation has been radical. So the plot on the left is a plot I borrowed from IPCC, the United Nations organization, the intergovernmental panel that deals with climate change, that got the Nobel Prize for Peace a few years ago for their work in climate change. So every few years they do an assessment report, and they gather the results of all climate modeling communities worldwide, and they try to compare them and come up with concrete conclusions. And you see they started in the mid-70s, and then there was the first assessment report at the end of the 80s, second, third, and now we're at the assessment report 5. And you see how the complexity of the models have evolved. So we just started with atmosphere, land, and ocean models, and then eventually we added aerosols because they have a strong influence on the radiation that is heating up the planet. The carbon cycle was included. Now most models include dynamic vegetation. So if it rains, you produce more crops, or if it's dry, you lose crops. So that has feedbacks on the climate cycle. And now, for the first time, the models are including full atmospheric chemistry of trace species, and also ice on land. And then on the right is the evolution of resolution, of modeling resolution. And this is most important in the horizontal level because the atmosphere is in layers, but you see that we went from maybe 100 kilometers down to 30, and we're pushing the boundaries now to go in the exascalar of computing even to 10 or 5 kilometers, with the eventual goal of resolving cloud convection. So you see how big a difference it makes, even if you go from a model resolution of 90 to 30 kilometers in the figure. So to summarize all this, on the plot of the on the left, so you see that computer power keeps increasing, but at the same time we're increasing model complexity by including more processes in our simulation. Then we're increasing model resolution, so you see that Typhoon in the beginning of the modeling community's efforts was just a few grid boxes, and now we can simulate exact clouds and their convection. But the idea then in the future is not only to go to the limit of maybe 1 kilometer, that is the limit where sort of global models can operate because of turbulence. But the idea is to have an ensemble modeling, so run multiple models and produce like a Monte Carlo experiment, for example. This is already done for weather forecasting, but it's very costly, and you cannot do it for the climate scale of decades. But that's the idea for the future. So this is the curve we are on today, the green curve, and the idea is we need to speed up our models to be able to achieve what we plan for tomorrow. So with current technology and with it's not a matter of throwing more computing, it's just impossible to do all this. We need to accelerate model development. And unfortunately, the reason it's not possible is because there's an absolute power limit. You can't just keep growing computers because they consume more and more energy, and also there's a limit to the scalability, so how much we can break up the problem. And this is a plot by ECMWF, is their future projections as they go down in model resolution, so meaning higher resolution, and the number of computer cores that they use to simulate their problem. You see there is a sort of range that we can work in. So the bottom gray band shows for one model, and then you have an ensemble. The green is this curve, so we operate in this regime, and this is where we are at now, and this is the where we're looking to go to in the future, so exascale computing. And the idea is to reach this level of ensembles with high resolution is impossible without improving our capability, modeling capability. So technology can't take us there by itself. We have to work on actively improving the models. So, and at the same time, as we increase the resolution and the complexity, so we want to store more variables at high resolution, we have a problem with how much data we're generating. And we are...
This is global models.
Yes. Sorry?
This is global.
So it can be global or regional.
No.
You mean this one?
You need so much computational resources for the global?
Yeah, so ECMWF, they have a global model. They are actually the European Center for Medium Weather Forecasting. They do, if you look at the BBC weather forecast, they are the ones that provide the information. So right now they run at 12 kilometers globally, and they have models running for the next few days. Then they run at high resolution for the next few months, and so forth.
And this data is used for the weather prediction. Yes.
This?
Yes.
You mean this one?
Yes.
Okay, so they run medium and long scale models, both. But the weather prediction community is a step ahead from climate in terms of resolution. So this is where the climate community wants to go. And okay, Japan is already trying to do this. They have this air simulator now with their new supercomputer, the K. They want to have a global climate model running at 5 or 4 kilometers for 150 years. And that's definitely in the realm of where ECMW is operating right now. Okay. So So how much data are we generating? So I have here an example for a single field. So let's say we want to store temperature around the globe. And then we have 30 levels, and we aggregate them. And then we want to do a small ensemble of 10 models. That's very modest. Like right now, EPCC runs dozens of models, and maybe more in the future. And maybe you just want to change the parameter set, not just change the model. But let's say 10 models for 60 years, which is the equivalent of 22,000 days approximately, and just keep one field per day. So we're not keeping at the time resolution of our model, which is minutes, we're just keeping one measurement per day, maybe the average, or at 100 kilometers. Again, this is not for the future, this is right now. So in total, that means you have 6,700,000 fields, and at 100 kilobytes, that means you have 626 gigabytes of data. So that's one single field, and we have hundreds of variables. We have not just temperature. We have wind speed, precipitation, cloud cover, aerosols, chemistry. So you see, we are deep in big data territory here. And so this brings a lot of challenges: how to capture the data, clean them, curate them, integrate everything, how to store, process, visualize. And so not only do we have strong computing requirements, we have very strong data storage requirements and the need to understand. So big data is as a term is thrown around a lot, but I use big data in this talk to describe data sets that are too large or too complex to be worked upon using common community tools. So you cannot just copy it in your laptop and in like 2 minutes produce a plot. And climate science is a big data domain, as I just hopefully demonstrated convincingly. So we have to use large repositories. Usually these are federated. So that all these climate scientists, they upload their data on repositories, and they are not easily moved. So the operations, the analysis has to be migrated to the storage. And then, because again of the size and the complexity, we need HPC to do the analysis. It's not just simple mathematical operations anymore. So this makes it even more important to have proper metadata and for discovery and provenance. So I'll now move on to 3 use cases from the Bison project, trying to directly address these challenges that I just presented. The first is the use of GPUs to accelerate climate modeling. So this plot from the top 500 supercomputers is an initiative that sort of monitors the top supercomputers in the world and sees trends as they evolve. So you see in the past 15 years or so, we've seen a huge adoption of accelerator technologies, GPUs and many integrated core like Xeon Phi, in the top supercomputers in the world. So nowadays, more than a third of the performance of the top supercomputers is actually given by accelerators and not graphical GPUs. And unfortunately, climate models for multiple reasons are not taking this, they're not taking advantage of these technologies. So, and this is expected to be even more important as we go from petascale to exascale computing. Because of the power limitations, we're seeing more and more hybrid computing on the node level or on the system level, and so we're not anymore in the regime that was in the past, that every 2 years you would just double the clock speeds or even double the cores, and you can just keep getting performance improvements for nothing. So you have the same model, maybe you work a little bit on the scalability, but the technology would drive the speed up. Now we have to actively work on applying models on hybrid or more complex architectures. So this is the project that is undertaken by scientists here at the Cyprus Institute. So we're working on stiff OD solvers, so ordinary differential equation solvers, mapping them on GPU architectures, so accelerators. These are used then to calculate the chemical kinetics of the atmosphere, so the chemistry, and this is by far the most demanding computationally part. It takes more than 60 or even up to 80% of the time, because it's you have to solve for each grid box in your model all the chemical interactions at every time step. And as you increase complexity, adding more chemistry, this becomes the limiting factor. So the idea is some of the equations are stiff, causing imbalance, so we want to transfer this on the accelerators, and then that's not enough. Then you have to keep in mind that this goes inside a global climate model. So again, you have to balance workloads to be able to run at a high speed.
How many chemical components do you use in this model?
Okay, so it depends on the, so but for example, a simple case would be 140 compounds and maybe 300 reactions. But each one of those is one or more ODEs that have to be solved, so each reaction. And then you have to solve them as a global system because each compound, so it's a huge matrix that you have to.
I understand.
Okay. So a second example is regional forecasting and opening the data from the model. So the Cyprus Department of Meteorology is also part of this team. They using the weather research and forecast model to do predictions on Vicim resources. So they have computing time and support from the project. They produce forecasting data for the general public. So they work with the scientists to fine-tune their model for the region to achieve the best possible accuracy, and then we help them to translate their model output into human and machine readable standard formats like XML or JSON, and these are open to an API, and they are available through the Cyprus National Data Portal as well as the Vicim repository. And we also help them set up a little website, so their data are also available online, and they are giving us their station observations real time, so we not only serve it to the public, but we help them store it and for the future. And then the final use case is post-processing and visualization. So models produce raw data, so it's just strings of incomprehensible to humans. And then the first step is to create the metadata, so both to provenance and integration, and then using these two together is to actually produce, to visualize this data, and like, I mean, this is what humans understand, this is what machines understand. So the idea is to have in situ massively parallel post-processing and visualization, exactly because of the huge data sets. And this is facilitated by a number of, by all the services offered by Vicim. So we have data storage services that are open to all the user communities in Vicim. You have compute resources, so HPC, cloud, and grid, and then they're application specific to each community. So there's regional data sets. There's the live access server, which is, I'll just show a brief a demo at the end, that allows people to visualize big data sets on their browser and produce images for scientific publications, even get scripts out to do this on their own processing software. And then we have workflow software tools and training data sets. So Vicim developed this live access server based on off-the-shelf technologies, but we populated with data that are useful for the climate scientists in general, but specifically we're also targeting regional data. You can visualize graphs on the fly, request custom datasets, get the data, get a chunk of the data. If you just want a timeline, for example. I'll show more at the end. And these are some of the examples now of the post-processing visualization output from within Bison projects. So we had a group using WorkChem to simulate dust transport, and we used Vapor to visualize that. On the same sort of domain, another group used WRF to look at clouds, weather. So that's another image on the right there. So we use ParaView to remotely visualize the output of the EMAG global model. EMAG is also the model we're developing the ODEs on, so the GPU acceleration. So this is distribution of moisture around the globe, and scientists can use this in real time. And also, some people are using CFDs, so computational fluid dynamics. This is a backbone of atmospheric circulation, and they're trying to see if they can create better parameterizations using OpenFOAM. So this is another visualization using Visit. So I just have a list of related projects that I'm not going to go through. You can look at the slides later. So it's my view that Bison has strong impact on the climate and weather forecasting communities of the region in all of the areas that we are focusing on. So climate modeling, weather forecasting, air quality simulations, and then we're combining all the HPC grid data resources to facilitate this. And there's opportunities for users that have not, so not individual groups, but now users can collaborate using the code repositories that Bison is providing. There's a training site with a wealth of material. There's a virtual research environment, which is highly productive, targeting all three user communities, and we're hoping to see also interplay between the communities. And we're linking to global efforts, like the IPCC, for example, to be of use to the global scientific community. So I'll just quickly show the VRE, the Bison VRE portal. So you have the three communities, and here you can find all the services offered for its community, dataset codes, workflows, and also request access to HPC resources if your research is in one of these communities and falls in the countries supported by the project. And finally, this vSIM live access server. Okay, the resolution is very bad, but I'll try to give you a quick example. So this is a graphic here. You can see the region that is supported on the left, and there's a lot of data sets that you can visualize. Let's take an example for winds, meridional wind. So this is the wind speed around the globe, and then if you want to zoom in on a specific region, you can just select it, have it deployed, and you have the region here. You can compute averages, minimum, maximums. You can get line plots of specific points, and then the nice thing is that you can output this on different applications, including Google Earth, and so forth. You can change dates, times, and of course you can get the images and use them for your application. So we have lots of data sets, both regional and global. So that's all I have. Thank you, and I'm happy to take any questions.
Yes. What model do you use for the climate prediction for the military region?
Okay, so we support a number of models. So have users using a number of models. So we use WRF climate, TVREX-CM. We have green climate, which is mostly dust, but it's a climate model using the MM5 dynamical core, and a couple of others that escape my mind right now. But if you're interested in specifics, you can go to the VRE website, and you can see all the codes that are supported. So Vine, DRS, ACS, these are the codes that we support. And of course, if someone, if a new user wants something else, we can always go with. But we did a survey of all the users in the region, and these are the ones that were requested at the time. So we support them on multiple sites for each.
Thank you.
So my question is about the examples you said you're using it in weather forecasting, right? About the sample you produced about the...
Yeah. So for example, when you hear 90% chance of rain, they run 100 models and 90 produce rain.
They're independent, or they communicate, maybe they give some information between the samples.
So right now, the way it works for most, there's people doing what you're saying, trying to branch at different simulation times or perturb the models as they run to see a change. But what is usually done right now, just start with a different set of emission parameters and you run them through the simulation. So either different sets of parameterizations, for example, how the physics are in the model simulation, how they are parameterized, or you just shift a little bit the initial conditions within the uncertainties because the weather forecasting relies on the current knowledge. You just play a little bit with the uncertainties and see how that would affect it in the future. But the idea is to do that for climate models, and people now are talking about super ensembles, so thousands of models running together to find extreme cases that happen very rarely but are still possible.
Questions? And then no more questions. Let's thank Theodoros again. Georgios Artopoulos is going to talk about digital culture heritage. Listen.
Hi everyone, I'm the responsible for the digital cultural heritage community at the VICM project. The cultural heritage community has some particularities, so we have different challenges, and therefore my presentation will be slightly different from those of my colleagues. The main problem we have with cultural heritage, of course, is the fact that it's not, our question is not quantified, it cannot be quantified. So what do we study? What's the question? Is it about studying the products and the results of human culture historically? How do you approach this issue? So obviously there are different methodologies and totally different tools and approaches, and within this larger scope of the field of cultural heritage, we have different smaller questions with their own world of tools and inquiries. The main issue with cultural heritage is that the scholars and the researchers active in the field, obviously, they don't know that what they can do with computation. They don't know that they need computational power other than a simple computer. Therefore, most of the applications and what you could find out there, they are single-threaded and are applications that they wouldn't benefit whatsoever with the use of high-performance computing. So the whole process in the context of engaging the communities in the region in the context of the PRACE project has taken longer than expected. There has been a slower start to the other communities. Of course, cultural heritage is very important in the region. This is needless to say, how rich the area is in cultural heritage and important. Having this different approach to the other communities, I consider very important to place ourselves as a project and identify what are the differences from what is it has been done already in the context of the European Union funded research. Most of the activities that of the past that have been active in the field of cultural heritage, they focus on what we call digital humanities. And digital humanities can or cannot be benefit from HPC, depending on the approach. As most of the researchers in the field come from the humanities, and they limit themselves in understanding the use of the computer for their research as digitization. But computation is something much more than just documenting what is out there and representing it. So this is how we try to approach this problem and actually find the people who are actually active and are operating in such areas that would really use computation. And these areas are of course, computer vision for image recognition, machine learning for remote sensing and electrical resistivity tomography automation, for structure from motion, photogrammetric techniques application, and VR experiences. The other initiatives, large-scale initiatives that exist in the European Union is, of course, Europeana, which is like a huge repository of linked data, which is very, very useful, of course, and important for digital humanities. It's Ariadne, which is a unified repository that provides mostly access to data via a map interface, via mapping the data, and it focuses mostly on archaeological data. And of course, it's of an international scope, but it's mostly focusing on Western Europe. And Daria, which is again in digital humanities infrastructure. So in respect to the tools and the services, it's very similar to the PRACE, because Daria also provides tools for organizing data in a sensible way and workflows, but it's mostly, one could say, grounded on digital humanities rather than heritage sciences. So, what are the areas that we are looking at in the context of PRACE? They are, of course, online data management systems and access to repositories like digital libraries with support of metadata and integration of image previewers and, for example, OCR tools. It's tools for online visualization. like interactive visualization of reflex transformation imaging files, interactive 3D models, and virtual reality tools and environments. And most importantly, for tools for end infrastructure, meaning the use of HPC, access to HPC facilities for data processing, for unsupervised feature learning that can have great benefit in photogrammetric techniques, image classification, semantic referencing, and georeferencing. Now, if we go into one of these areas, for those of you who are not familiar with these terms, digital library is a collection of collections of electronic knowledge resources developed and maintained in order to meet the totality of information needs for a given user population. So by providing services to our users in the region who have the data, like BVL, for example, who have hundreds and thousands of books, but they don't have the capacity or the expertise to manage them, to organize them and manage them in an efficient way. We provide, after we work with them, we provide them guidance on how to organize this data. With regards to online visualization tools, the tools that we are looking at for digital cultural heritage in VISIM include the integration of viewers for 3D models, for PTM models, which are basically the files that are produced from reflex transformation imaging. Do you know what is RTI? What is the reflex transformation imaging? I suppose other than J and Phil, nobody knows, right? Yes, okay. It's a very complex file which is produced by the combination of multiple images of the same object taken from different angles, which are combined in such a way that when you access the file, these photographs are taken under controlled conditions, and when you combine these photographs and you access the file with the use of these viewers, you can actually have a 2D image which has dynamic light, for example. So you can move the light around your object, or you can change, you can integrate spectral imaging information in the file. So this has great potential, and it's used for the study of very small objects that have their importance is on the texture of their surface. As you can imagine, by controlling the light, we can reveal the depth of the texture. So researchers and scholars that are active in that area, or they are in need of this tool, they can actually reveal like inscriptions that are very difficult to be read with the bare eye. And we have, of course, to continue, several other viewers, like for special kind of panoramic images that are of very high quality, different viewers for different types of file types of 3D models, like OBJ converters to X3D, or using WebGL online platforms. And to move on to the third use case, as I said, data processing is very important for structure for motion. Structure for motion is a photogrammetric technique that is used currently as an alternative or to complement the use of laser scanner for the documentation of physical object of various scales, of course, from a small earring to a building or to the walls of a medieval city, like in Nicosia. And the way this technique is operating is by combining having the program understand the angle from which a series of photographs was taken in order to reconstruct from this series of photographs a 3D model of the object that is captured in those photographs. As you can imagine, this is a very computationally intensive process because the program, the code has to identify and match points in space, and from the difference in lighting and in the position of these points onto the image, code reconstructs the geometry of the object. And in particular, in the context of PRACE, one of the applications we are supporting is using these techniques in order to reconstruct digital terrain models. As you can see here, so they have thousands of images taken by drones, and they need this pipeline, this workflow, in order to document the surface of the area of interest. Another use case, which again is based on computer vision, is of course OCR for complex scripts of complex letters and shapes, like Hebrew, for example, manuscripts. And also our fifth area is electrical resistivity tomography. And in this field, the problems that the researchers are facing relate to the mapping of geological formations and stratigraphy, the identification of underground zones related to water and mineral resources and geothermal activity, the detection of pollution zones and pollutants that flow in the Earth's subsurface, the extraction of quantitative information for buried archaeological relics, and the spatial and temporal monitoring of the subsurface resistivity. The files they are collecting with the use of electrical resistivity tomography gear are of this kind. And as you would imagine, computer vision would really thrive in this area because it's very difficult even for the human eye to map and identify the specific patterns that would have them to be interpreted in this.
So what is the resolution of this meter? Kilometers, meters, hundreds of meters?
It's in meters.
Meters.
Yes. And lastly is bioarchaeology. You heard from Ed the importance of sesame and some overview of how these synchrotron activities and facilities can be used for the study, for research in bioarchaeology. And similarly, the interpretation then of the results can be computationally intensive. We have in the context of PRACE, we have a training portal that you can see here. Which includes all kinds of training material from instructions for the creation of digital repositories and the management of data to more technical training material for example, Drupal or using other programs and platforms to very specific information.
Cournia, as I understand, is an electronic catalog program, yes?
I don't know. Yes. Two very specific ones, like this one, which actually is for data analysis, which is very topical to humanities inquiries. Now, the main activity that we have had in the last year in the context of PRACE was the integration of Clouder, which is a data management platform created by NCSA, and its adaptation to the needs of our user community. Clouder supports many data format and multiple research domains, and this is why it was chosen to be our main application-wide service platform. Because as you saw in digital cultural heritage, there are huge differences in needs and the tools and workflows between the different groups, as there is no one question per se that they are trying to answer. And it's in terms of its operation, it basically can be considered that there are 3 steps. It's the pre-processing step that is happening in the background when a user uploads data, a data set or some file, the processing and the previewing of this data. And on Clouder, users, they can actually, as all data management platforms, they can upload, download, search, visualize, and actually interact with the metadata that are associated with the data sets. The data sets that, in terms of types and formats that we are currently have integrated in our platform include 3D models, where there are specific extractors that they clean up and prepare for visualization the file, scan books with their associated metadata, the OCR algorithms that are embedded currently only with Latin characters.
What is this OCR algorithm is?
The one that is currently integrated on Clouder is proprietary code, but we are currently working on building an OCR extractor that will be based on data. Image and text and sound files with their metadata, and as I mentioned earlier, vectors commission imaging files. The data organization on Clouder, the options that they have, that the user has when after the sign up process is to create a data set and upload files and assign metadata to those files, or even upload massively metadata that through an XML parser will be mapped on the files, and of course people and users can add tags and comments on these files. Users can create. Yes, we can. They can also organize them as collections or as in spaces. The extractors that are currently integrated support big game files. Those are the files that I described to you earlier that are produced or generated from text information imaging photogrammetric techniques. And in addition to that, we have an experimental tool that generates like an embossed, slightly 3D version of the 2D image. So actually users, after uploading the two-dimensional photograph, they can generate this 3D model and rotate around to observe better the inscriptions and the texture. PDF files, MP3 sound files and videos, and of course images. For the future, what we are planning to do is to optimize the code that reads the 3D file so that we can actually upload even larger scale models and with more detail, and to allow users to upload non-scanned documents and have them being searchable, like PDF docs and text files, and also to integrate some metrics for video files. Now, I would like to take you quickly through the list of applications that we are, so that you can have an idea of what kind of applications we are servicing. So we have 4 from Crete in Greece, working on computer vision for the management of electrical resistivity tomography files, and for the use of advanced structure for motion that are accelerated, they accelerate the combination of photographs for the generation of 3D models. We have a couple of users that will be building their digital libraries of books on our platform. And then we have also another user from Bosnia and Herzegovina who will be basically using our HPC federated facilities for running their convolutional neural networks for advanced image processing. And also another application which focuses mainly on geolocation of digital assets. Then we have an application, this one from Oxford University, which is basically for the study of Ptolemaic inscriptions, and they will be using Clouder for the creation of a digital library of their RPI files of Ptolemaic inscriptions. and a few on the use of image recognition for OCR, for optimized OCR tools, and I will finish with our colleagues from BA, with whom we are collaborating for the development of a toolkit and a workflow of tools for the creation of virtual reality applications, which can be accessed online over the web. Okay, everyone is pushing me to finish, so I will stop here. Thank you very much.
If you have any questions for George, then please find him outside.
We're behind on schedule, so we have like 15 minutes of.
Yeah, there's another 15 minutes.
Thank you, Stadium.
And yeah, if you have questions for George, put him down.
George, you can